this is another Laplace transform, inverse Laplace transform question, and we have determine the inverse Laplace transform of g of s. Just as a quick remark, I use g of s actually to sort of signify given in the question, and I use f of s to sort of specify some sort of structure in the formula sheet usually. In this case, I'm going to change that slightly. This is sort of a tough one in that the answer is not the first thing you do actually is just sort of consider that it is a s plus 3 divided by this polynomial here, s squared plus 2s plus 3. Now, usually what I sort of say is factorize it, find the roots. But if you try that out, you realize that, that's not so easy. What are the roots of that? There's nothing obvious there, and even if you are using the minus b formula, you might sort of not find a satisfactory answer there. So in these sort of questions, actually, if there's obvious roots or roots that you can sort of pick out relatively quickly, then go for it. But if not, you sort of think, oh, hang on a second here. What I'm going to do here is actually rewrite this equation in the form compatible with the first shifting theorem. And what I'm going to do is let a equals minus 1. So if you sort of look at your tables, I'm going to rewrite the g of s in this form here. Now, this is what I mean by the formula sheet. So I'm going to let f of s, let it equal f of s minus a. So I'm just going to slightly rewrite the formula. So we have g of s down here. I'm going to let a equal to minus 1, so that makes it s plus 1. F of s plus 1. Now, let's sort of think about where I came up with that. Essentially, s plus 1 squared equals s squared plus 2s plus 1. And what sort of made me think of that is this 2s here. Okay? So s squared plus 2s plus 1 is s plus 1 squared. So essentially what I'm sort of saying is we can actually write this as s squared plus 2s plus 1 plus 2. Have plus 1 plus 2 instead of the 3 there. Okay, so essentially what I'm saying is we can write g of s in this form here, f of s plus 1. We can have s plus 1 squared plus 2 at the bottom. And also above we can rewrite s plus 3 as s plus 1 plus 2. Okay, now the sort of method in my madness, if you sort of go back here and just sort of think ahead to what and sort of look at the Laplace transform tables, you sort of see where I'm going with this. What I want to do here, I have fs plus 1, but I want to find f of s. And this is because I want to find out f of t shortly. Okay. The reason is that that's part of the inverse Laplace transform. So I'm going to replace this expression here. I have s plus 1 plus 2 divided by s plus 1 squared plus 2. That's f of s plus 1. Just as a matter of interest, what would that make f of s? S plus 2 divided by s squared plus 2. Simple enough. Okay, that's f of s. And if that's f of s, what is the inverse Laplace transform of this? Now, I sort of said here it's not immediately solvable, but it's actually not a hard problem at all. It's actually, let's scroll down here a second. We can write f of s as s, here we are, divided by s squared plus 2, and we can write plus 2 divided by s squared plus 2. And these are sort of very straightforward structures that we sort of see in the formula sheet. We can write S as K1S divided by S squared plus A1 squared, and likewise K2A2 divided by S squared plus A2 squared. K1 and K2 are just scaling coefficients. It's just like half times or 2 times. It's just a scalar coefficient. So what we could do here is find out the inverse Laplace transform of f of s, and it would be in this form here: K1 cos A1t plus K2 sin A2t. Okay. Now, so let's just try this out. K1 is necessarily 1. Okay. And A1 squared, well, that makes that the square root of 2. Likewise over here, A2 squared, that makes that 2. K2 times A2 equals 2, and immediately follows that K2 is also the square root of 2. So if you think K2 A2 is equal to 2, and you know A2 is also square root of 2, that makes K2 the square root of 2 also. So as in, the square root of 2 times the square root of 2 is 2. That being K, well, K2, and that being A2. It's actually where these sort of scalings come in. So, f of t, let's go down here now a second. So we've actually found out the inverse Laplace transform of f of t, and it is cos square root of 2t plus the square root of 2 times sine square root of 2t also. Okay, so that's f of t. Okay, now remember earlier on, this is just so we've actually gone a long way. So what I just sort of backtrack here, g of s was in this form here, f of s minus a. And the inverse, I'll scroll down a little bit more here, and the inverse Laplace transform of f minus a is something from the tables. I sort of mentioned it there briefly, but I'm going to be a bit more explicit about it here now. This is in e to the power at times f of t. Okay. Now, we have f of t, it's up here, and we also know e to the power of a of t, because remember we said f, we're going to make this s plus 1, or f structure in that form. G of s is structures in this form here, f of s plus 1. So, now all we have to do is find out essentially we have it done basically. And determining the inverse Laplace transform g of t, recall that g of t equals e to the power of at times f of t with a equal to minus 1. So it's essentially, that's f of t there. This is e to the minus t. There it is. That's the answer there. G of t equals e to the minus t cos square root of 2t plus square root of 2 e to the minus t sine square root of 2t. What I'll do here just briefly is I'll just sort of zoom in a bit. See if I can zoom in a bit just to sort of see if you can get the answer a little bit legible. I'm very concerned about, oops, gone too far. I'm very concerned about the lack of legibility on my presentation. So there it is again. And we'll call it a video.